Okay, we're underway. We have a simple model with reasonable performance. Where do we go from here? Well, to make further gains, we need to stop treating the model as a black box. We need to open it up and get visibility into what it's learned, and more importantly, where it still falls down. And then we can begin to look at some ideas for how to improve it. One important way to gain understanding of our trained models is to inspect the model weights. Which features are strong positive indicators for each relation, and what features are strong negative indicators. The RelX module contains a function called examine model weights that makes it easy to inspect. So here I show results for just 4 of our 16 relations. And in general, I think the features with large positive weight are pretty intuitive. So for the author relation, the biggest weights are author, books, and by. For film performance, we have starring, alongside, and opposite. By the way, I was a little bit puzzled when I first saw alongside and opposite, because I thought that those are words that would naturally appear between the names of 2 actors, not between the name of a film and the name of an actor. What I did was I wrote a little bit of code to pull up the actual examples that caused these weights to wind up being large. And what I realized was there's a very common pattern, which is like X appeared in Y alongside Z. So X and Z are actors, Y is a film. X appeared in Y alongside Z. So you have Y alongside Z, that indicates that Z is an actor that appeared in film Y. And I think something similar happens for opposite. So it does make sense that these are strong indicators of the film performance relation. For has spouse, we have wife, married, and husband. I think this makes perfect sense. The one that's a bit surprising is adjoins. So for adjoins, we have Cordoba, Talux, and Valais. It's odd to see specific place names here. They certainly don't seem to express the adjoins relation. I wonder if anyone has a guess what's going on. I was really puzzled by this. And so again, I wrote a bit of code to find the specific examples that contributed to this result. I looked for examples where the 2 entity dimensions stand in the adjoins relation, and these terms, these specific terms, appear in the middle. And when I looked at the examples, I realized that what's going on is that it's very common to have lists of geographic locations. So A, B, C, D. And in such lists, it's not uncommon that just by chance, A and C or A and D stand in the adjoins relation. Maybe it's a list of provinces in a country. And of course, some of those provinces are adjacent to each other. So if A adjoins C or A adjoins D, that will tend to make B appear as a positive indicator for the adjoins relation, and especially if the corpus just happens to contain several such examples. So I think that's what contributed to this puzzling result. The features with large negative weights look a bit more haphazard, but I think that's not surprising. It's kind of what you expect for this kind of linear model. By the way, you can fiddle with the code that prints this out, and here it just prints the top 3. But you can fiddle with the code. There's actually a parameter that tells it how many of the top of the list to print. And so you can print much longer lists. And for many of the relations, the top 20, even the top 50 features all look very plausible and intuitive. And it's quite satisfying to see those results come out. Another way to gain insight into our model is to use it to discover new relation instances that don't currently appear in the KB. In fact, as we discussed last time, this is the whole point of building a relation extraction system, to augment a KB with knowledge extracted from natural language text at scale. So the decisive question is, can our model do this effectively? We can't really evaluate this capability automatically because we have no other source of ground truth than the KB itself. But we can evaluate it manually by examining KB triples that aren't in the KB, but which our model really, really thinks should be in the KB. So we wrote a function to do this. It's called find new relation instances. And you can go look at the code. Here's how it works. It starts from corpus examples containing pairs of entities that don't belong to any relation in the KB. So these are what we described last time as negative examples. We'll consider each such pair of entities as a candidate to join each relation. So we'll take the cross product of all of those entity pairs and relations. We'll apply our model to all of those candidate KB triples, and we'll just sort the results by the probability assigned by the model in order to find the most likely new instances of each relation. So we'll find the candidate KB triples that aren't currently in the KB, but which the model believes have really high probability of being valid. So let's see what we get when we run it. Here are the results for the adjoins relation. Notice that the model assigned a probability of 1.0 to each of these pairs. It is totally convinced that these pairs belong to the adjoins relation. But the results are, well, let's be honest, the results are terrible. Almost all of these pairs belong to the contains relation, which, by the way, isn't actually one of our 16 relations, but intuitively, they should belong to a contains relation, not the adjoins relation. You could make a case maybe for Mexico and Atlantic Ocean belonging to the adjoins relation, but I mean, to be honest, even that one is a stretch. One other thing worth noting, whenever the model predicts that X adjoins Y, it also predicts that Y adjoins X. You might, for a moment, think that this shows that the model has understood that adjoins is a symmetric relation. Unfortunately, no, that's not what's going on. It's just an artifact of how we wrote the simple bag of words featureizer. That simple bag of words featureizer makes no distinction between forward and reverse examples. So it has no idea which one comes first and which one comes second. And that will be true for asymmetric relations, just like for symmetric relations. So this is not a very promising start. It's, I mean, we saw a very good, pretty good quantitative evaluation for this model. So this is a little bit surprising. Let's see what we get for some other relations. So here are the results for the author relation. And these look a lot better. Once again, all of the probabilities are 1. But this time, every single one of these predictions is correct. Well, not quite, actually, because the book is supposed to appear first, like Oliver Twist, and the author second, Charles Dickens. So this first one actually is correct. The second one is backwards. It has the author first and the book second. Our model is completely ignorant of order, so it's just as likely to put things in reverse. But if you ignore that, if you're willing to imagine that we could easily fix that, then the results look great. We could put all of these triples right into our KB, and we'd have a bigger and better KB because of it. This is relation extraction at its finest. This is what we wanted. Here are the results for the capital relation, and it's a similar picture. All of the probabilities are 1.0. The ordering is frequently reversed. It's very haphazard. But if you put that aside, the results look very good. You could quibble perhaps with Delhi here. I mean, the capital of India is really New Delhi, but New Delhi is part of Delhi, so, you know, it's close. Still, overall, I think this looks really good. Let me show you one more. This is the last one I'll show. These are results for the worked at relation. And here the results are more mixed. So we have Stan Lee and Marvel Comics. Sure, if you can say that Elon Musk worked at Tesla Motors, then you can say that Stan Lee worked at Marvel Comics. And while we're at it, Genghis Khan worked at the Mongol Empire. Sure, why not? But the rest are nonsense. So why? What happened here? Well, when you encounter surprising and mysterious results in your model output, it's really good practice to go dig into the data and investigate. And this is called error analysis. And I want to show you a couple examples of that now. So first, let's see if we can figure out what happened with Louis Chevrolet and William C. Durant. First, let's look up the corpus examples containing these two entities. I'm only going to look up the examples that have them in this order. I should look them up in the other order as well. And as a matter of fact, I did. I'm just not going to put that on the slide. I'm just going to focus on what happens in this order. So I'm going to look up these examples and print out what they look like. And here's what we get. There are 12 examples, and they all look identical. Actually, I didn't print the full context here. If you look at the code closely, you'll see that I'm printing the suffix of the left and the prefix of the right. So there's more context further out on left and right. And if you did see the full context, you would realize that the examples do differ slightly, but they're very, very similar. They're near duplicates. I mentioned this last time, that this is one of the warts of this data set. It contains a lot of near duplicate examples. And I think this is an unfortunate consequence of the way the sample was constructed, the way the web documents that this corpus was based on were sampled from the web. And it seems like that's bitten us here. But it still leaves a question, why? Why did that repetition lead the model to predict that this pair belongs to the worked at relation? Because it doesn't look obvious that that's the right relation here. I suspect that it's because of the word founder, because X being a founder of Y strongly implies that X worked at Y. And actually, we can check this. It's not that hard to write some code to inspect the weight that was assigned to the word founder in the model for the worked at relation. So here's a little bit of code that does that. And sure enough, in the model for worked at, the word founder gets a weight of 2.05, which is pretty large. If you look at the distribution of weights, it's a relatively large one. I forget exactly, but I think it's in the top 10. It's a relatively significant, quite significant feature for this model. So that's what happened. We've got 12 examples. Each of them is contributing a sizable weight. And the result is that the model is completely convinced that that this is the right, that the worked at relation holds here. By the way, I didn't check, but I'm confident that the model for the founders relation will also predict that the founder relation holds here. An understanding of what went wrong here could help to stimulate some ideas for how to fix it. I have some ideas. I think I won't give them away, but I hope this underscores the value of error analysis. You really want to understand, when you see weird results, you really want to understand what's going on in your data that led to these weird results. Let me show you one more example that has a bit of a different flavor. Let's look at what's going on with Homer and the Iliad. I wrote a little bit of code to investigate this one too. And I'm not going to show the whole investigation, but I'm just going to cherry pick the most informative results. So one thing that I noticed is that there are a lot of examples for Homer and Iliad. In fact, there are 118 of them just in that direction. There's more in the reverse direction. That's impressive, but again, by itself, it doesn't explain why worked at looked like a good prediction. By the way, I did check to see if it was the same explanation as last time, a lot of near duplicates. It's not. That's not what's going on here. But the next thing I did was to write some code to count up the most common middles that join Homer and Iliad across these 118 examples. And so that code looks like this. And here are the results. And there was one middle that strongly dominated, and it's apostrophe S. So as in Homer's Iliad. So that makes sense, because clearly the possessive can indicate the author relation. You expect to see Homer's Iliad and Jane Austen's Pride and Prejudice and many other similar formulations. But the apostrophe S can equally well indicate the worked at relation, as in Tesla's Elon Musk or Microsoft's Bill Gates. So this apostrophe S is really highly ambiguous. Just to confirm that this is actually significant to the result that we saw, let's check what weight was assigned to apostrophe S in the model for worked at. So this code is similar to the code on the previous slide, but this time we're looking for the weight for apostrophe S. And it turns out that the weight was 0.58. Okay, it's not a huge weight, but it's not small either. And this feature occurred 51 times across the corpus. So I think that's what happened. We had a, non-trivial amount of weight that got added up 51 times, and we wound up with a really big contribution and the model feeling really confident about this relation. So again, thinking about this problem might suggest some strategies for how to reduce that ambiguity. The fundamental problem here is that apostrophe S is highly ambiguous. A good question to ask yourself is there other information in the sentence that could help to distinguish the author relation from the worked at relation? And I think there is. Again, I don't want to give too much away, but I think there's other evidence in these sentences that could help to tease apart these two relations. And this kind of error analysis is really indispensable to the model development process. Now, for the homework and the bake-off, we're going to turn you loose to find ways to improve this baseline model. And there are a lot of possibilities. One area for innovation is in the feature representation we pass to the learning algorithm. So far, we've just used a simple bag of words representation, but you can imagine lots of ways to enhance this. So you could use word embeddings, like the glove embeddings. You could use a bag of words representation that distinguishes between forward and reverse contexts. You could use bigrams or longer n-grams. You could leverage the part of speech tags that we have in the corpus or information from WordNet. Much of the early work on relation extraction relied heavily on syntactic features, so maybe try that. And so far we've used features based only on the middle phrase, the phrase between the two entity mentions. You could also try using information about the entity mentions themselves. For example, the entity types. Or you could try deriving features from the left and right context. There are a lot of possibilities for richer feature representations. There's also a lot of room for innovation with the model type. Our baseline model is a simple linear model optimized with logistic regression. That's a good place to start, but there are many other possibilities. If you want to stick with linear models, you could use an SVM, and sklearn makes that easy. Or you could experiment with neural networks. You could use a simple feed-forward neural network as a drop-in replacement for our linear model. Or since examples can be of variable length, you might consider a recurrent neural network, like an LSTM. If you go this way, you'll have to think carefully about how to encode the input. If the input is just the middle phrase, things are probably relatively straightforward. But if you want to include the entity mentions or the left and right context, you might need to think carefully about how to demarcate the segments. Or you could use a transformer-based architecture like BERT, although the quantity of training data that we have available here might be a bit small. I think all of these are potentially interesting and fruitful directions for exploration, and I think you can have a lot of fun with this.